Maybe you have no.
One. Chemistry of solutions. First, I will explain about solutions. The main solutes in a solution are cations and anions. The main cations in surface water, for example seawater, river water, and groundwater, are Na+, K+, Mg2+, and Ca2+. These four account for more than 99% of all cations. In agricultural areas there is also NH4+. The main anions are Cl-, NO3-, SO42-, HCO3- and organic anions. Agricultural land also contains H2PO4- and HPO42-.
Okay, do you have any questions? If no question, I will go next.
Hydrate. For example, when sodium chloride crystals dissolve in water, water molecules first bond with Na+ and Cl-, and then get between them. As a result, the Coulomb attraction between them weakens. These two ions then diffuse into the water as hydrated ions. The water bound to these ions is called hydrated water. Thus, in aqueous solutions, all ions are hydrated.
This Google English hydration is not good. Hydration. One for hydration. Okay. All
hydration
in water is hydrated.
You can learn more about the Coulomb force by doing an internet search on Coulomb's equation. The main points are as follows. The Coulomb force between two charges is proportional to the product of the two charges and inversely proportional to the square of the distance between them.
Okay, now, do you have smartphone now, students?
Yes, I was saw video in YouTube about Coulomb equation, bro.
Internet, Coulomb force.
Yes.
Coulomb law.
I was saw video on YouTube about Coulomb, and then I know about minus and positive, negative and positive, just for interaction between the molecule, bro.
Yes, but
right?
For more confirmation, now by using your smartphone or PC, could you search Coulomb force or Coulomb's law? I give you 2 minutes. Please check the equation of the Coulomb's law using your smartphone now. In 2 minutes, okay? You can find very easy.
Yep. Okay, bro.
Okay, can you find Coulomb equation? Very simple equation. Very famous physical law. physical equation. You found Coulomb's equation?
Yes,
Yes or no?
Yes, I found, Prof. I respond, but maybe in Bahasa,
Yeah.
not in English. I
Equal,
found the video in YouTube.
yeah. Okay. So very easy equation. Okay, I'm going to the next.
By searching for the keyword, simulated hydration, on YouTube, you can easily find easy-to-understand videos about hydration and salt dissolution.
Sorry. The keyword should be simulation, hydration. Okay. Now, can you? Okay. Now I will search. Hydration and simulation. You can find simulated hydration. This is potassium. This is chloride. You can find many simulations related to hydration. Okay, later you can look more about the simulation of the hydration. Okay, next. Okay.
So, why do water molecules bind to ions? This is because water molecules are polar molecules. The oxygen atom in a water molecule has a charge of about -0.6. On the other hand, a hydrogen atom has a charge of around +0.3. Water molecules as a whole are electrically neutral. Such molecules are called polar molecules. Therefore, oxygen atoms in water molecules are attracted to cations and hydrogen atoms to anions by Coulomb attraction.
Then next, Indonesia.
Jadi, mengapa molekul air mengikat ion? Hal ini karena molekul air adalah molekul yang bersifat polar. Atom oksigen dalam molekul air memiliki muatan sekitar -0.6. Di sisi lain, atom hidrogen memiliki muatan sekitar +0.3. Molekul air secara keseluruhan bersifat netral secara listrik. Molekul semacam itu disebut molekul polar. Oleh karena itu, atom oksigen dalam molekul air tertarik ke kation dan atom hidrogen ke anion oleh daya tarik Coulomb.
Okay, you understand the content?
Okay, Prof. We understand, Prof.
Yes, thank you.
Relevant knowledge: food can be heated in a microwave oven because water molecules are polar molecules. Detailed mechanisms can be easily found through an internet search.
So I every day use microwave or oven for cooking. You also use microwave. So the mechanism of the microwave heating, you can easily find through internet. Okay, going to the next.
Pengetahuan yang relevan. Berbagai senyawa anorganik dan organik juga memiliki gugus O. Perhitungan kimia kuantum telah menunjukkan bahwa semakin besar muatan positif atom hidrogen dalam gugus O, semakin besar kemungkinan atom hidrogen tersebut terdisosiasi sebagai H+. Sebagai contoh, struktur kimia etanol dan asam asetat serupa, tetapi etanol adalah alkohol dan asam asetat adalah asam. Perhitungan kimia kuantum menunjukkan bahwa atom hidrogen dari gugus O asam asetat memiliki muatan positif yang lebih tinggi daripada atom hidrogen dari gugus O etanol, karena dilepaskan sebagai H+. Maka atom H dengan muatan positif asli yang lebih tinggi akan lebih mudah dilepaskan.
So I think this content is somewhat difficult to understand. Then could you study by yourself by looking at the here? Today I will not explain in more detail because this is not so related to soil chemistry. Okay, going to the next. Sorry.
As Coulomb's law shows, the ionic force to attract water molecules depends on the type of ion. A. For divalent ions, the force used to attract water molecules is greater than for monovalent ions. B. For ions with the same valence, the smaller the ion radius, the greater the attraction towards water molecules. This is because a smaller ionic radius allows water molecules to approach closer to the ion center of positive charge, thereby reducing the distance between the two charges.
So, according to the Coulomb's law, A and B is very easy understood.
A and B above can be easily understood from Coulomb's equation. In summary, the attractive force of cations on water molecules is as follows. Cs plus less than K plus approximately equal the image NH4 plus less than Na plus less than Li plus less than Ba2 plus less than Sr2 plus less than Ca2 plus less than Mg2 plus less than heavy metal cations less than L3 plus less than Fe3 plus for cations from Cs plus to Ca2 plus. The only force that attracts water molecules is the Coulomb force. For cations from Mg2 plus onwards, in addition to Coulomb forces, chemical bonds, coordination bonds, occur between the cation and the oxygen atom of the water molecule.
Okay, so this is attractive force of cations in the environment. Magnesium, heavy metals, aluminum, iron is very strong bind with force. Sorry, how
Halo, tes. Pak
please
Eko,
someone
maaf.
mute, please.
Yes, Pak Eko. Min. Mute. Pak Eko. Wait a moment, Prof. Matsui. We will confirm to Pak Eko for mute the.
Maybe someone should mute.
Yes, Prof. Nur was tell to Pak Eko. And confirm to Pak Eko.
Okay. So I will start again.
Relevant knowledge: when iron 3 chloride or iron 3 nitrate is dissolved in water, it becomes a very acidic solution. This is because the bond between Fe3+ and O in the hydration water is so strong that the O bond in the hydration water is weakened and H is released as H+. As a result, iron hydroxide ions are formed. Similarly, aqueous solutions of Al3+ salts are acidic and aqueous solutions of heavy metal cation salts are weakly acidic.
So maybe you know that iron salts show strong acid. So this is the mechanism.
Relevant knowledge: in the classic chemistry experiment, determination of Ca2+ concentration in aqueous solutions containing Mg2+ and Ca2+ by EDTA titration method. The pH was set at a
Sorry, so do we have this experiment using EDTA? Please answer yes or no. EDTA titration for calcium and
EDTA.
magnesium. Yes or no? Please answer.
No, Prof. I don't know.
No?
Maybe
You don't know.
other.
Okay. In Faculty of Science, Department of Chemistry, very old experiment by using the EDTA titration. Okay. Again.
relevant knowledge: in the classic chemistry experiment, determination of Ca2+ concentration in aqueous solutions containing Mg2+ and Ca2+ by EDTA titration method. The pH was set at around 12-13 and Mg2+ was precipitated as magnesium hydroxide. Since Ca2+ is not precipitated at this time, the Ca2+ concentration can be determined by the EDTA titration method. In other words, Mg2 plus precipitates as magnesium hydroxide at lower pH because it has a greater bond strength with O- than Ca2+. The difference between these two cations is similar to the difference in the hydration strength of the two ions. In other words, the bond strength between the cation and the O atom of the water molecule is approximately proportional to the bond strength between the cation and the O atom of O-.
Okay, do you understand? So, please look at this. Magnesium precipitate as hydroxide, pH higher than 10. They will not precipitate as hydroxide. Heavy metals, aluminum, iron, precipitate as hydroxide.
In hydrated cations, there are 4-6 water molecules bound directly to the cation. This is called primary hydration water. In the case of cations with tightly bound water molecules, the secondary hydration water is bound around the primary hydration water. As a result, the diameter of hydrated cations is larger for cations that are strongly bound to water molecules. For example, as shown in the diagram below, the ion radius, without hydration water, is Mg2 less than Na less than K+, while the hydrated ion radius is Mg2 greater than Na greater than K+.
Okay, this ionic radius, but the hydration radius greater for magnesium than sodium, potassium. Magnesium ion attract water molecule, very strong, and many water molecules are bound to magnesium. Then become very large hydrated cation.
The above diagram schematically shows the ionic and hydrated radii of Mg2+, Na+, and K+. The inner circle, actually a sphere, shows the size of the ion and the outer circle shows the size of the hydrated ion. The size of the outer circle indicates the size of the hydrated ion as well as the bond strength of the hydration water. For example, the hydrated ion radius of Mg2+ and the bond strength of hydration water are much larger than those of K+.
Okay, do you have any questions?
It is known that the interlayer distance of montmorillonite in air-dry state is Mg2+ type greater than Na+ type greater than K+ type. This is because these cations are stored in the interlayer as hydrated ions.
Wait, do you know this phenomenon? You can ask any question.
Na+
anytime.
rich montmorillonite soil is susceptible to landslides when rainfall causes swelling between the montmorillonite layers.
related to
Prof.
landslide.
Matsue,
Yes.
maybe I have the
Okay.
question, Prof.
Okay.
Monmorilonet, I think Monmorilonet is the soil with the clay is apa keras, ikatan yang keras, Prof. Nur. Maksud saya kira seperti itu. Kenapa bisa terjadi longsoran seperti itu? They so easy with the landslide. Why Monmorilonet so easy make some landslide, Prof? I think Monmorilonet is clay with the powerful aggregate.
So, because monomoronite has interlayer cations such as sodium, potassium, calcium, magnesium. But of course, magnesium, but in nature, if sodium is main interlayer cations of natural monomoronite, sodium is easily sodium contains more hydration water than potassium, and also magnesium and calcium is divalent, so they can bind to the layers. Then difficult to expand in natural conditions. But in case of sodium, because sodium has much more hydration water than potassium, monovalent cation. So sodium rich monomoronite easy to cause landslide. Just landslide? No?
Landslide is longsor, Prof. Tanah longsor. Yes, this is landslide.
So, for example, do you know tofu? Tofu? Do you know tofu? Or protein? Protein. Aggregate. If you added calcium ion, magnesium ion, because they are divalent cation. Magnesium, calcium bind protein molecules to cause aggregation. But in case of sodium, proteins disperse. Similar to the phenomenon, monomoronite, sodium type monomoronite easily disperse and cause okay. My explanation was okay.
Okay, Prof. Thank you.
Okay. You can also ask your professor in Indonesia. Okay, so I go to the next.
Asterisk radiocesium ions are strongly bound to 2-to-1 type layered silicate clay minerals such as mica and montmorillonite. This is due to the easy desorption of Cs plus hydration water and the size of non-hydrate Cs plus that fits into the hexagonal pores of these minerals. Hydrated Mg2 plus cannot penetrate zeolite pores with small holes. Magnesium hydroxide and magnesium oxide are used as laxatives. This is based on the fact that Mg2 plus retains hydrated water in large and strong quantities.
Okay, this is their related knowledge. Okay, next subject.
1.2. Ion pairs and complexes. In the following description, it is assumed that you know that all dissolved chemical species hydrate in aqueous solutions. In other words, hydrated Na plus in water is simply denoted as Na plus in water.
Okay, because all ions are hydrated. Sodium in water. In this case, sodium Na plus is hydrated.
For example, when calcium chloride is dissolved in water, most of the Ca and Cl exist in the water as Ca2+ and Cl-. However, some exist as water-soluble ion pairs such as calcium chloride plus and calcium chloride, and their concentration is higher at higher calcium chloride concentrations. For example, when using calcium chloride to estimate the COC from the amount of Ca2+ adsorbed, the COC will be too high if the presence of CaCl+ is not taken into account. This overestimation can be avoided by performing a thorough rinse after Ca saturation. It is known that the adsorption strength of negative charges is calcium chloride plus greater than Ca2+.
Sorry, not COC, but CEC, cation exchange capacity, CEC. They are ion pair. In addition to Ca2 plus and Cl minus, CaCl plus and CaCl2 zero exist in high concentration of calcium chloride solution.
Unlike complexes, ion pairs have water molecules between the ions. In other words, they are bound to each other by Coulomb forces as hydrated ions. The difference between ion pairs and complexes is illustrated below. The area between the inner circle and the outer circle, ellipse, is hydrated water.
So this is the difference between ion pair and complex. In complex, ligand is directly bind. But in case of ion pair, hydrated calcium and hydrated Cl minus is attracted and bonded. This is the difference between ion pair and complex.
Alkaline metal cations and NO3- do not form ion pairs or complexes. These ions exist only as single hydrated ions in aqueous solutions.
So this is very important that Na plus, K plus, and NO3- do not form ion pairs or complex. These ions exist only as single hydrated ions in the water. This is very important.
Details about complexes and complex ions, charged complexes, are explained in high school and university chemistry textbooks. Nitrates are used when preparing aqueous solutions of heavy metals because NO3- does not chemically bond with heavy metal cations and is therefore highly soluble in water. Most nitrates are very soluble in water. Likewise, most alkali metal cation salts are highly soluble in water. On the other hand, Cl- forms ion pairs, complexes, and sparingly soluble salts with many heavy metal cations. Common examples are calcium chloride plus, silver 1 chloride, and lead 2 chloride.
Cl- and NO3- looks similar, but in the viewpoint of complex or ion pairs, Cl- form many ion pairs and complex. But NO3- usually does not chemically bond with heavy metals and even with iron and aluminum.
Various ion pairs, complexes, and compound ions are dissolved in surface water. For example, in seawater, iron forms complex ions with fulvic acid and is soluble in water. If there were no ligands such as fulvic acid, there would be no dissolved iron in seawater. This is because the pH of seawater is approximately 8.1, so that iron precipitates into iron hydroxide. Fulvic acid forms a water-soluble complex with iron, allowing plankton to absorb iron as a nutrient source. Fish eat plankton for growth. In other words, if fulvic acid is not present in seawater, fish growth will be hampered. In addition, because fulvic acid is supplied from forests to the sea via rivers, deforestation has a major impact on coastal fisheries.
So this is a very famous story. Do you know this phenomena? Student, yes or no?
Yes, maybe deforestasi, Prof.
Yeah. The conservation of forest is very important.
Yes, very important for the sea.
Yeah. So next, I going to the activity.
.3 Activity and concentration. High school chemistry textbooks in Japan are of a high standard and contain up-to-date information. The contents are a good reference even for chemistry researchers. I assume that the situation is the same as in Indonesia. However, there are some things that are not mentioned in the textbook, namely, quantum chemistry, and activity. You can find out more about activity in diktat books or by searching on the internet. Here I will explain the meaning of activity.
High school chemistry is very high level, but it does not contain quantum chemistry and activity. About the activity, you can study by using textbooks or internet. Then here I will explain the meaning of the activity. Uh, 30 years ago, soccer, Indonesia, soccer was stronger than Japan. But now Japan is stronger than Indonesia. So this is a
If 11 of your relatives, friends play football against 11 members of the Indonesian national team, which team do you think will win? The number is the same, 11 people. However, there is a huge difference in player strength. In this example, the number of people is the concentration, and the strength of the players is the activity. Assume the average strength per player of the Indonesian national team is 0.9, and the average strength per player of your team is 0.3. Is this assumption valid? Then,
become 9.1. Your team 0.3. But 0.1 by 11 is 3.3. This is a activity, concentration. Same concentration, but different activity.
in the above equation, 0.9 and 0.3 are activity coefficients, 11 is concentration, and 9.9 and 3.3 are activity. Here you can see that even though the concentrations are the same 11, the activities are significantly different. Activity coefficient x concentration equals activity. The expressions in the diktat book are as follows. Activity equals activity coefficient x concentration. Here you must once again realize that the molar concentration is simply the number of solute per unit volume. Activity is also called effective concentration, and it greatly influences the actual chemical reaction. In other words, activity is strength in soccer. What determines a chemical reaction is not concentration but activity. For example, calcium sulfate, CaSO4, dissolves only 2.4 grams per liter in distilled water, but more than 10 grams per liter dissolves in 1 mole per liter NaO3. The calcium sulfate dissolution precipitation reaction is as follows. Calcium sulfate left pointing over right pointing arrows Ca2++ SO42- in the equation above. The reaction to the left is the reaction that occurs when Ca2+ and SO42- collide. In a 1 mole per liter NaO3 solution, these collisions are hindered by the high concentration of Na+ and NO3-, and the collision frequency between Ca2+ and SO42- decreases. As a result, the reaction rate to the left decreases so that the solubility, reaction rate to the right, increases. For example, calcium sulfate is difficult to dissolve in 1 mole per liter calcium nitrate solution or Na2SO4 solution. This is called the common ion effect.
Could you understand? Calcium sulfate dissolve much in sodium nitrate solution. But difficult to dissolve in calcium nitrate or sodium sulfate. This phenomenon is called common ion effect. Common ion effect. Do you know common ion effect? Students, yes or no? Please
I
say.
think the explain in the Google Translate before the common ion effect.
This is the common ion effect.
Yes.
In case of calcium
Cannot.
sulfate, cannot dissolve into calcium nitrate or sodium sulfate. Common ion CaSO4 cannot dissolve in calcium nitrate or sodium sulfate. This is called common ion effect. Okay, please study by yourself after this lecture what is common ion effect.
For a given ion I, if its activity is I, its activity coefficient is gamma I, and its molar concentration is C, then the following formula applies. I equals gamma I C, 1, for example. The molar concentration of Ca2+ is expressed as Ca2+. The solubility products studied in high school are as follows. Case B equals Ca2+, so 42-2, however. The solubility products listed in special data books are expressed in terms of activity. Case B equals Ca2+, so 42-3.
Tapi suaranya lantang.
Okay, so in high school,
Tapi kayak nek anggo aku kurang kurang.
in
Mas
high
Fahmi.
school, sorry, so can I speak? In high school, equation 2, KSP equals the product of concentrations of calcium and sulfate. But in special data books or in university chemistry, we must use activity, not concentration, activity.
For example, Ca2+ activity is expressed as Ca2+. It is correct to express the equilibrium constant in terms of activity rather than molar concentration. This is because the equilibrium constant expressed in terms of activity remains constant if the temperature is constant. But the equilibrium constant expressed in terms of molar concentration, official name, concentration equilibrium constant, changes depending on the concentration and coexistence ions. The concentration equilibrium constant is sometimes included in data books, but in this case, ionic strength, explained later, is always included. The solubility product is a type of equilibrium constant. The equilibrium constant expressed in terms of activity is also called the thermodynamic equilibrium constant. However, it is usually called the equilibrium constant. The equilibrium constant expressed in terms of molar concentration should be called the concentration equilibrium constant.
Okay, this is very important. The equilibrium constant by using activity is simply called as equilibrium constant. But the equilibrium constant expressed in terms of molar concentration should be called the concentration equilibrium constant for high school students.
By combining 1, 2, and 3, the following formula is obtained. CASP equals gamma Ca, Ca2 plus, gamma SO4, SO42 minus, equals gamma Ca gamma SO4, Ca2 plus, SO42 minus, equals gamma Ca gamma SO4 CASP equals gamma Ca gamma SO4 CASP. 4. The activity coefficient gamma varies between 0 and 1. In an ideal solution, 0 concentration, gamma is 1, CASP equals CASP, and the higher the concentration of coexisting ions, the smaller the value of gamma. Furthermore, when there is coexistence of divalent ions, gamma decreases significantly. For example, the values of gamma Ca and gamma SO4 in seawater or 1 mole per liter nano-3 solution decrease to about 0.2. So from equation 4, CASP approximately equals 0.04 CASP. Since CASP is constant, CASP is approximately 25 times CASP. In other words, CASP expressed in molar concentration in seawater is 25 if the value in distilled water is 1. The concentration of Ca2 plus and SO42 minus increases by 5 times. 5 is the square root of 25. High school textbooks do not mention that CASP changes significantly due to the influence of surrounding ions. Ideographic period.
Could you understand about the activity? Okay, so this is the final of the activity.
The valence and concentration of coexistence ions are expressed by ionic strength. Furthermore, the activity coefficient can be calculated using the Debye-Huckel equation as a function of ionic strength. Details can be found in the Diktat book or by searching on the internet. Software for calculating the ionic strength of a solution and the activity coefficient and activity of each ion has long existed. Asterisk note: coexistence ions means ions that exist together in a solution.
So, about the activity. So, the understanding is maybe very difficult. So, I recommend you to study with textbooks or with internet for more understanding.
Weak acids and pKa acids are classified into weak acids and strong acids. However, there are only a few strong acids, such as hydrochloric acid, HCl, and sulfuric acid, H2SO4. All organic acids can be classified as weak acids. For example, citric acid and oxalic acid. Inorganic acids such as phosphoric acid, H3PO4, and carbonic acid, H2CO3, are also weak acids. In addition, the functional groups of soil components such as clay minerals and humus, C-O, Al-O, Fe-O, COO, Therefore, knowledge of weak acids is very important in soil chemistry.
Oleh karena itu, pengetahuan tentang asam lemah sangat penting dalam kimia tanah.
Okay, so weak acid. The knowledge of weak acid is very important for soil chemistry. So I will explain about the weak acid and
Weak acid.
pKa concept in next week. Okay, so could you study by using the PDF file I sent Professor? Now you have the file, okay? So I hope you to study about the what is weak acid, what is pKa, is why pKa is important in understanding weak acid and also through chemical reaction. Okay, thank you very much for today. So do you have any
Arigatou gozaimasu, Sensei.
Okay, thank you very much, Professor Matsue. Yeah,
Thank you.
although we are still in some difficulties, how do we can understand about actually for the hydration about the sodium and then potassium as a monovalent and also the radius of the hydrate ion of potassium and natrium sodium different, and also about the valence like monovalent and divalent. I think that is important for us. And then about how do that the soil dominated with smectite or montmorillonite, with sodium rich, so it can more easily to landslide. I think very understand. And then how about the the role of the protein? The role of the protein is the positive charge. Also maybe we will understand more about this. The role of the protein. In relation to the interlayer space of the montmorillonite. Yes. And also we today we also study also learn about the complex and also the ion pairs, in relation to the hydration. I think very interesting. And then also about the seawater in relation to the iron. Yes. And because of the seawater pH around 8.1, and so it is the condition that the iron will be precipitated in the iron hydroxide, sorry. And also we also study about the ionic activity. Ionic activity. That the ionic activity is the ionic concentration times by the activity constant. Activity constant. And I think when I was the bachelor student, I also study about the ionic activity and also the ionic strength. That ionic strength depending on the valence and also coexistence. Yes, I think very important for us. And then we want to make more material for this, for our student. Yes, because you know that in the syllabus of the chemistry, the student a lecturer give the student concentration, not activity. So I think it is good suggestion from you, from Professor Matsue, for us how do we can improve to give material about the ionic activity and then ionic strengths. And thank you very much. And to next week for the final material from you, we hope that we can understand and then we can learn about the weak acid, then important things about the weak acid in soils. Very interesting, very
Thank you very much
useful for
that.
us.
Thank you very much for your details explanation.
Yes, you're welcome. And then, very thanks from me to you. Okay.
Thank you very much.
Thank you very much. Yes. Okay. So,
Okay.
please you
Yes.
give the
So, right.
yes. Mhm. Closing remark from you, please.
Okay, thank you very much, staff and students. Okay, thank you.
Yeah. So
See
thank
you
you very much, student.
see you next week. See you next
Yes.
week.
Yes.
Hi.
Thank you. Okay.
Okay,
Thank you,
I
Prof. Matsui.
I go out.
Thank you, Sensei.
Thank you, Professor.
Siap.